Okay, good afternoon. And today we would like to discuss about the unit number 3. So it starts with the introduction to IC technologies. Okay, so here we start with a simple understanding about microelectronics evaluation. So how the electronic circuits evolved starting from invention to making a more sophisticated ICs. Okay, so this microelectronics evolution is possible only because of the miniaturization and advancements in fabrication process. Okay, so because of these two things, microelectronics has got a tremendous evolution is observed. Okay, so let us start with the simple. Let us start with a simple transistor, a single transistor, which is invented in 1947. Okay, and initial days this is treated as a discrete type of component, which means whenever we want to design a particular circuit, if you want to design a particular circuit, what you have to do is that we have to individually place all the components, right? We have to place all the components, make the necessary connection between them, make the necessary connections between them. So that's what we normally do. So this kind of approach is called a discrete component representation. Okay, so generally is single components will be available throughout the circuit. But from 1967 onwards, integrated circuits came into existence. What does it mean? So that means instead of taking the individual components, something like this, we take a common base. Just we have to modify this base according to our requirement. For example, someplace we want to form a transistor here, you can form a transistor here. You can form a resistor here. So whatever the components that we want to do it, we can place it in the same substrate. Just we have to modify that one. Okay, for example, I want to write a 3-dimensional view, something like this. For example, this is what an IC, for example, or it is a silicon, for example. Okay, for example, it is a silicon. So the entire thing is actually a silicon. Okay, so on top of it, what we do, we place one component here. We can modify this place for a transistor. We can use this place for resistor, capacitor. Okay, so on top of it, we can provide the wiring, everything that we can do. So therefore, we can use the same base material. But here its base is not the same. So this is an individual component. This is individual component. This is individual component. But fix it in some breadboard type the device and make the necessary connection between them. But there is a problem with this kind of approach that is called, in the descriptive nature, we find some problems. So because as the number of components are increases, the area taken by the circuit will be very, very large. Okay, so therefore what we do, we go for integrated circuit approach. Therefore this is called IC approach. Okay, in this IC approach, we can place more number of devices in a small area. So that is evident that you can see in this table. Okay, for example, if you talk about small scale integration. Okay, so therefore, of course, ICs are classified into different types depending upon how many number of components that we can place. Okay, for example, if you're able to place only 10 transistors, for example, in a chip, so therefore IC, or we can also call it as a chip also, one and the same. There is no difference in it. Okay, so therefore what we do, if you're able to make only the 10 transistors in a substrate or a base material, and this IC, we normally call it as small scale integration. Agreed? Similarly, if you are able to provide 100 to 1000 transistors in an integrated circuit, then we normally treat it as medium scale integrated circuits. Okay. Similarly, if you're able to provide the number of transistors in an IC is from 1,000 to 20,000, for example. Okay. So more than that, if you're not able to do it, for example, then all these ICs are called large scale integrated circuits. Okay. So, and it is also possible to provide more than 20,000 transistors up to 1 million transistors. Okay, 1 million transistors. It is possible. So this type of ICs are called VLSI circuits. VLSI integrated circuits. Okay, so as I mentioned that this evaluation or the changing of the range to another range of the number of transistors in an IC is only because of the miniaturization and advancements in fabrication process. For example, if you want to provide, for example, if you want to provide 1 million transistor, 10 million transistor, if the fabrication equipment is not at all acceptable, then if it is not accepting the number of transistors for accommodation, then obviously we are not into enter into this ultra large scale integration. It's not possible then. So therefore, obviously, advancements in the fabrication process also play a crucial role. Whatever we have theoretically, that means it is possible that the length of the transistor, the size of the device is possible to reduce theoretically, but the same thing need to be fabricated in reality with the help of fabrication process technique. If the fabrication is not fabrication process is not allow us to do this kind of miniaturization, it is not possible to move from one IC technology to so one IC classification to another IC classification. Okay, so therefore miniaturization and advancements in the fabrication process play a crucial role to move from one integrated circuit to another integrated circuit. Okay, so if you're able to provide more than 10 million transistors, then we normally call it as giant scale integrated circuits. Okay, the question is that obviously one question will arise. Okay, so what advantage that I will get if I move from one particular IC classification to another IC classification? So because if then depending upon the number of devices that we can accommodate in a transistor, that decide what type of that decides what type of device we are fabricating or what type of device we are making. Agreed? That means if an IC consisting of a number of transistors, with that one, it is possible to make a certain kind of device only. So that is evident we can see in this table. For example, if you see that the IC consisting of only 10 transistors, then it is possible to make logical gates, flip-flops. We are able to do this one. We can make logical gates, AND gate, NOR gate, OR gate, XOR gate, or flip-flops also we can do. It requires only it requires only around the 10 transistors, not more than that. For example, if you have counters, for example, or if you're using the multiplexer, or if you're using the adders, then it requires more number of transistors. Therefore, it will become under the medium scale integration. Okay, for example, if you talk about a processor, for example, and ROM, RAM, all these things needs a large number of transistors. Then we have to rely on large scale integration. For example, the microprocessor have 32-bit and 16-bit and GHM. So these are the related processor related. So if you want to improve the processor speed, or if you want to improve the high performance processors, then automatically we go for VLSI circuits. So whatever the integrated circuit that we normally talk about, okay, the main theme is that accommodate more number of transistors in an IC. Okay, so but VLSI is popular because of the people are achieved a goal of millions of transistors in an IC. Therefore, people are using even if it is a giant scale, even if it is ultra large scale, people will call it as very large scale integrated design only. Okay, but whatever the concepts that we learn about the VLSI, the same concepts are applicable to ultra large scale or giant scale also. For example, the concepts that we talk about small scale integration. Okay, the same concepts are applicable to medium scale, LSI, VLSI, all these things. But the only thing is that how can we provide the connectivity between the transistors? And if you are reducing the number of transistors, okay, so if you're increasing the transistors means automatically more number of space it consumes. But the constraint is very less for that one. Area constraint is very less. For example, in this way, in this given small area, I'm able to provide 5 transistors, for example, 5 transistors. It is also possible to use the same area with the help of 10 transistors. With the help of 10 transistors, provided we have to reduce the size of the transistor. That means we focus or we play only with the length of the transistors only. Okay, by reducing the length of the transistor, okay, so we can accommodate more number of transistors in the same area only. Okay, so therefore this kind of mechanism will be used when we move to the one integrated circuit to another integrated circuit. Okay, so therefore the bottom line from this slide is that the microelectronic evaluation is based on the miniaturization and advancements in the fabrication process made us to move from one integrated circuit technology to another integrated circuit technology. Okay, so depending upon the number of transistors in an IC will decide the type of the integrated circuit. Okay, clear? Okay, fine. Now, as I mentioned that the basic component in an IC is a transistor, right? Agreed? That means, of course, okay, forget about for the time being, just to you remove that for whatever it may be the component it is, it doesn't matter. For example, the ICs are also classified into different types. As I mentioned that based on number of transistors, it may be a small scale integration, large scale integration, medium scale integration, very large scale integration, all these things we have seen. But depending upon the type of component that we place, okay, depending upon the type of component that we place, the ICs are classified into different types. Okay, so depending upon the what type of transistor that we are using in an IC. For example, if you're using the bipolar junction transistor, okay, throughout the IC that we are using only the bipolar junction transistors only to make any particular circuit. Okay, it is possible to use the CMOS devices also. It is possible to use the BiCMOS also. It is possible to use the gallium arsenide transistors also. Okay, so depending upon a type of the transistor that we are using in an IC, we can classify the IC technologies. Okay, so if you're using the bipolar junction transistor, it is called BJT technology. BJT technology. If you're using this one, it is called CMOS technology. If you're using this one, it is called BiCMOS technology. It is called gallium arsenide technology. So we normally call it as in the industry. If you go and people will talk about the CMOS technology, we use it to fabricate the devices, or maybe gallium arsenide technology, we have used it to do this one. Not only these two things, but other things are also there. Okay, the basic classification or basic difference between the IC technologies is based on type of material that we are using again. Okay, so what type of material that we are using for your transistor? So for example, if you're using the silicon is the material that you're using for your transistor, then it is called silicon based technology. For example, if you're using the gallium arsenide based material for your transistor, then it is called gallium arsenide based technology. Sometimes we normally use carbon nanotube FETs, carbon nanotube also. So therefore, CNFET technology. This is called CNFET technology. Okay. So therefore, what I can say that if we talk about an integrated circuit, these integrated circuits are classified into different ways. Okay, one is called uh, one is based on the number of transistors. Okay, the second one is type of transistor. The third one is type of material for transistor. Type of material for a transistor. Agreed? How the ICs will be classified depending upon the purpose. Agreed? Is there any doubt in this? Can you please let me know through the chat? Integrated circuits are classified into different types based on the number of transistors in an IC and what type of transistors that we are using in an IC and what type of material that we are using for a transistor. So based on that one also we can see IC is all about. Yeah, based on silicon. So okay, so for example, if you're talking about the transistor, for example, bipolar junction transistor. So we need a material to form this bipolar junction transistor. That's what we are going to see in the coming classes. So generally we use a silicon material. Generally we are going to use a silicon material. Same bipolar junction transistor it is possible to realize with gallium arsenide also. So it is possible to realize the gallium arsenide also. Okay, so therefore the material is the same for different transistors. Okay, that's what kind of material that we will use, that we'll see in a short while. Okay, but the IC technology classification based on the material is possible. IC technology is based on type of a transistor can possible. IC technology classification is based on number of transistors also possible. Okay, fine. Now let us look at more detail about the silicon CMOS technology. So as we have seen previously, we have different type of technologies are there: bipolar junction transistors, CMOS, BiCMOS, and gallium. In our syllabus, we have silicon CMOS IC technology we need to talk about. Okay, so therefore we talk about silicon CMOS based technology. Agreed? So this is what we need to focus on this one, but it's a very, very popular one when compared to other technologies, other IC technologies. What is the reason why the silicon CMOS technology is very popular for fabricating of devices? Okay, so the first of all, what exactly meaning of the silicon CMOS technology? That means if you take an IC, it consisting of both the NMOS transistors as well as PMOS transistors. Both transistors will be there in an IC. Okay, for example, if you take bipolar junction transistor, we take BJTs, either it is in the PNP transistor or NPN transistors. Okay, but we don't want to use this bipolar junction transistors in our class. We focus mainly on CMOS related devices only. Okay, the reason is that the devices which are manufactured based on the silicon CMOS technology has got high performance. So the high performance circuits can possible to implement by using this one, and it's very, very important one is cost effectiveness. Okay, so very with the low price that we are able to make VLSI circuits. We don't want to spend a lot of money to make VLSI circuits. Okay, so therefore, so because of these two reasons, why the silicon CMOS technology is popular when compared to other technologies that are available. Okay, so for example, if you consider a RISC processor, for example, okay, so it needs that it has to execute 35 million instructions per second. So this is a very high throughput rate actually. Okay, so per second, how many number of instructions need to be executed? Normally we want to make an ICs for the processors, designing of the processors, right? So it has to process the commands whatever we give. If the processor has an ability to execute 35 million instructions per second, it's a very high computational devices, we normally call it as. Okay, so that kind of things are necessary for advanced in the day-to-day life livelihood for doing the different things. Okay, so this is what the throughput that we want to have. Okay, for example, but this is also not sufficient. The demand is increases day by day. Okay, therefore people are trying to go for 100 million instructions per second. They want this kind of throughput. Okay, so therefore what they have to do is that they have to ultimately opt for another IC technology that is called silicon BiCMOS technology. People will try to use this one. Okay, so therefore, if you want to improve the throughput rate of a processor, normally we need to change the IC technology. Okay, it may be from the silicon IC technology to some gallium arsenide technology, or sometimes we will go for the FinFET technology, or it may go for tunnel FET technology. Different type of technologies that are available. Okay, so the main reason to move from migrating from one IC technology to another IC technology is that we want to improve the throughput rate of a processor. That means the how many number of instructions that we can perform or that we can execute by the processor in a second will be defined for that. Okay. So therefore, yeah, I want to tell you one important point. What exactly meaning of BiCMOS? BiCMOS. What does it mean? Okay, BiCMOS means an IC consisting of not only the NMOS as well as PMOS. Okay, it is also consisting of BJTs also. It is also consisting of bipolar junction transistors. Okay, the IC consisting of all these devices. So then we take advantage of what is the advantage that we will get? The advantage of CMOS, the advantage of the BiCMOS, both we will use that one. Okay, the IC has got both advantages. So what is the individual advantage of the bipolar junction transistor? As mentioned here is that preferably BJTs are very high speed devices. So if you make any IC with bipolar junction transistor, it is high performance, high speed devices, we can call it as. Okay, the speed of the circuit is very, very high. Whereas if you consider the CMOS, for example, so what is the advantage of using the CMOS? CMOS is not that much high speed device compared to the bipolar, but the packing density and the power consumption of the CMOS circuits are very less. Okay, that means that more number of transistors can be accommodated in a given small area. That is possible with CMOS. Not only that, it is possible to reduce the power consumed by the circuit also. Okay, so in spite of the speed is less compared to the bipolar junction transistor, but it has got a good packing density and low power consumption. Okay, so therefore, but and one more thing is that so it takes a large area. So this is what the drawback of this one. But advantage is high speed. But here is advantage is packing density and power consumption, but so drawback of this one is a low speed devices. Of course, nowadays so many techniques that they have incorporated to improve the speed of the circuit, which is comparable to the bipolar junction transistor. In fact, more than that of the bipolar junction transistor also. Okay, so the bipolar junction BiCMOS is nothing but a combination of both bipolar junction transistors and CMOS devices. Okay, CMOS stands for complementary metal oxide semiconductor devices. It consists of both NMOS as well as PMOS transistors. Okay, we will see the classification of the transistors in a short while. Just you have to understand that from this IC technologies, especially the material point of view, the IC technologies are classified into two types. One is silicon-based IC technologies and gallium-based IC technologies. Okay, so when we move from IC-based, silicon-based to gallium arsenide-based technology, in order to improve the throughput rate. Okay, so for example, if you consider about the gallium arsenide, for example, so we can obtain more throughput rate, right? Agreed. So that's what we can say about IC technologies. Okay, so therefore we have started that the microelectronics evolution. Okay, and we noticed that uh, IC technology is the most important one. Okay, and these ICs are also classified into different type based on their requirements, based on their material properties, material, or based on number of transistor, based on type of a transistor. But whatever it is the case, for all these three classifications, we identify that the transistor is a most important component. Transistor is a most important component. Okay, so what are the different type of transistors are there in the market, and where we need to focus for better device manufacturing? Okay, so as we know that since from first year onwards we talked about the transistors. Means first we started with bipolar junction transistors. Everybody knows about it. Okay, so it has two flavors. One is NPN transistor, PNP transistors. So what is the one advantage of this one? As we have seen, high speed. What is the disadvantage of this one? Is the primary disadvantage, high power consumption. High power consumption. So the circuit consumes a lot of power. Okay, some other disadvantages are also there, but this is what we observe this one. Okay, so therefore, so in order to avoid this high power consumption, we have moved to uh, field effect transistors. Field effect transistors. Okay, so and one more thing is people normally we call it as the noise. Noise is very high for the bipolar junction transistors because of majority carrier transportation is observed. Okay, the carriers, the current carriers are majority carriers. Okay, that's what we observed in bipolar junction transistors. But whereas field effect transistor, minority carrier transportation is there. Okay, so not only that, it has got the biggest advantage of this one is more number of transistors can be accommodated in a small area, and another one is low power consumption. Low power consumption. That's what the basic advantage we need to move for field effect transistors. But there is also observed that there is a two flavors here: junction field effect transistor, metal oxide semiconductor field effect transistors. So whatever the advantage that we got, or whatever the disadvantage we got, is similar to that of bipolar junction transistor. Therefore, we don't want to focus on field effect transistor. We would like to move on metal oxide semiconductors. Okay, so therefore, junction field effect transistor not that much great performance compared to the bipolar junction transistors. That's the reason we move to metal oxide semiconductor field effect transistor. Here also we observe that two flavors are there: depletion mode type of transistor and enhancement mode type of transistor. So whenever we make a transistor, depending upon the channel, we can classify these things. Okay, at this point we'll see because we have a detailed discussion about this depletion mode and enhancement mode, and MOS transistors and PMOS transistors. We'll see later on. But we have to observe that we focus on the field effect transistor, the two metal oxide field effect transistor, and the two we need to consider only for enhancement mode type of transistor. Okay, and there are the two things are there. One is called N-channel MOSFET and P-channel MOSFET. So we talk about these flavors related things after some time. Okay, so these are the different classifications that we can make, and we are restricted ourselves to only MOS field effect transistors. Okay, this transistor can be enhancement type. Okay, so this point we will see in the coming slides. Okay, so let us discuss about something about mass transistors. Everybody knows that the name itself. So mass transistor, the name itself decide the what kind of structure that we have used. Okay, so it is actually a M stands for metal, O stands for oxide, S stands for semiconductor. So what is the current mechanism in this transistor means field effect mechanism that we normally considered or observed. Okay, so we observe that field effect mechanism. Sorry, this is not working. Highlighter. So the mechanism here is field effect mechanism. The transportation of the carriers is because of the field effect. Okay, so the first three words saying that what type of structure that we are using for a transistor. Okay, so this decides the type of the structure. This decide what is the mechanism for the transportation of the carriers. Okay, so such type of transistor that we are going to look at here. So this is the three-dimensional view of the mass transistor structure. We see that we have a source here, we have a drain here, we have a gate here at this point. Okay, so we have a gate here to this. So it is not possible to write it. It's a gate, actually. It's a gate. Okay. Now, in this three-dimensional view, we observe that one of the important or backbone for this transistor is this part. This part is very, very important one. Okay, this part. So therefore, because of this part only, it is called as a mass structure. Why it is called? Whatever the black color that you can see here. So whatever the black color that we see here, whatever the black color here we see here, this is called this. It is not visible. On top back coated the color thick line is there, no? So that is called, it's a metal. Under this one, whatever we can observe here, this is called an oxide. This is called an oxide. This is called a semiconductor. It is called a semiconductor. So this is the structure is important. So this structure, we need to understand this structure more carefully in order to develop the characteristics of this MOS transistor, right? So let us look at this MOS structure. Okay, we will go to the yeah. I forgot to. Okay, so let's look at mass structure. Okay, so mass structure. Okay, so it is a backbone to the MOSFET. Okay, as we have mentioned that it is a backbone to MOSFET transistor. Okay, or I can say that MOS transistor, right? Okay, so normally people will call it as MOS transistor. So let us understand that what is there here. So as we know that we have a three-dimensional view, something like this. On top of it, we have polysilicon, right? Also on top of it, we have some material is there. Okay, so this is what we observe, right? So this is the three-dimensional view of your mass structure, right? Okay. So what we observe that, okay, it's better to identify that on top of it, we have another material, right? Okay. It's very difficult to visualize this one unless otherwise three-dimensional view. I do one thing. Okay. Copy and I want to paste it here. So let us imagine that this is what actually this is your diagram. I'm talking about only at the middle part only. Okay, you please try to understand that we talk about only this middle part only. Okay, so this is the middle part. So what we observe here now. So here is actually here we have actually a semiconductor. This is what the pink color shows that the middle one, for example, is the green writing here. So green color is actually the middle one. So this is called an oxide. On top of it, we have a black coated material is there. Okay, so I don't know how to mention this one on top of it. So that's the reason why I'm writing here is some material on top of it. Please observe that a black coated material is there here. Okay, on top of it. Okay, so this is the structure that we normally focus on. Okay, so what kind of information that we can take it from the structure, all these things, we now look at that one. Okay, now fine. So generally it is a semiconductor, right? Generally it is a semiconductor. Why we need to take a semiconductor? So why can't we take a conductor? For example, consider this is a conductor. So consider this is a conductor. So what we observe that if you want to move a carriers from one end of this one to another end of this conductor, the carriers can transport from one end to another end. Okay, very easily by applying the potential difference between one end to another end. If you apply a potential difference, the carriers can move from this one. But there is no current controllability if you are using the conductor. Okay, so therefore the first very important point is that current controllability. What I want to do is that I want to make, for example, so that means, for example, if we want to do this one, we are able to apply the potential difference throughout this region, right? So entire this region that we have to apply. There is no doubt that we have to apply this entire region. Okay. So, but our requirement is that we want to provide the transportation of the carriers only at the surface. Only at the surface. Okay, not all the other region, other parts of the conductor. I don't want to do this kind of thing. Okay, if that is the scenario, the conductors are not able to do this kind of thing. Forget about insulators. Insulators cannot provide any kind of transportation of the carriers. Okay, as we know very well about it. But conductors can provide a transportation, but whatever the way that required is performed in that same manner. Agreed? Therefore, semiconductors will come into the picture. Therefore, we would like to use a semiconductors. Instead of conductor, we would like to move to semiconductors. So what will happen? Yeah, this is the same mechanism also observed here also. Okay, so our requirement is that we have to we have to provide the potential difference here. For the transportation of the carriers throughout, this is also bulk transportation is also possible. That means in all the directions, carriers can move from one end to another end if you provide the potential difference between them. Agreed? Yeah. But what is our requirement? Only at the surface it is required. That too, a minority carriers are required. It's very, very important. Minority carriers are required. Okay, so that means what I want to say that whenever you are using some kind of material, for the required way of transportation of the carriers, that is at the surface, we need to choose the material. And one more thing is that carriers must be a minority carriers. That carriers must be a minority carriers. So these are the two important things that we have to assume, we have to consider. Okay, so for these two requirements, a semiconductor is more suitable one. Semiconductor is more suitable one because the semiconductor has got a p-type semiconductor, or it can have an n-type semiconductor. So what we observe here now, we observe holes are majority and electrons are minority, right? Here in this case, the holes are minority and electrons are majority. Okay, so therefore, depending upon the type of semiconductor, the minority carriers will be available, and we can make them available at the surface. Okay, so the point of interest is here is that. So the point of interest is at the surface is important. I don't want other parts of the carrier transportation. Okay, therefore, in order to do this one, a small modification that we have to do. So what is that? We have to provide. Okay, I'll take another one. We have to provide an oxide layer on top of it. We have to provide an oxide layer on top of it. Okay, and provide there, I think, yeah, on top of it, we have to provide one conducting plate. Provide one conducting plate. So this is what the arrangement that I have done. Okay, so consider that this is a consider that this is the semiconductor. This is an oxide. We place a conductor here. So conductor is actually a metal. Metals are normally we use a conductor. Metals normally treated as a conductors. Okay, we use a metal there. Now, is it clear to all of you why we need to use the semiconductor? Okay, and why the purpose that we need to use oxide? Now we'll look at what is the purpose of using the oxide, what is the purpose of using the metal. Okay, now so we know very well about it now. What is the purpose of using the semiconductor? Okay, so now here what we need to do is that, so whatever available minority carriers throughout this bulk, normally the semiconductor we normally call it as a bulk. Okay, whatever the minority carriers are available, we need to bring them into towards the surface side. So in order to make these carriers toward the surface side, what we have to do, we have to apply a potential difference between these two. Okay, if you put it directly on top of the semiconductor, if you put a metal without oxide, okay, it is not performing this one. Okay, it cannot do anything actually. But if you put an oxide on top of it and provide the potential difference between these two materials, then the electric field will be developed from here. So the electric field is developed between the metal and semiconductor. As we know that the capacitor, how the capacitor will form a current within this one? Because of the displacement current. Okay, so how the displacement current will be possible? If you place one particular charge on one plate, other charge will be induced on the other plate because of the electric field. Okay, so that's the reason why, for example, if it is a p-type semiconductor, for example, what is the magnetic areas? Electrons. If you want to attract the electrons, what type of charge that I need to provide on metal? Anyone from the class? Can anyone tell me? I'm using the p-type semiconductor, right? And the magnetic carriers of electrons. I want to attract the magnetic carriers. In order to attract the magnetic carriers from the semiconductor, what type of charge that I should place on a metal? Exactly, positive charge. Okay, so we have to provide a positive charge here. So therefore, we have to provide a positive charge on top of it. That means what is the potential that I'm applying here? Positive charge. Okay, so because of these negative carriers need to be pushed towards the surface side, it is better to use a negative side at this point. Okay, because of this, the minority carriers are available under the surface. Minority carriers are under the surface. Okay, so therefore this is very important for the transistor operation. This is very important for transistor operation. The question is that how much voltage that we should apply here so that these minority carriers are attracted towards the surface. That voltage is called threshold voltage. Threshold voltage. Therefore, we have to apply some positive voltage, which is equal to the threshold voltage of a transistor. Then only the minority carriers are attracted towards the surface. Right? So this is the one case that we can call it. This is the one case. So this is a very popular case is called inversion. What we can call it as inversion. This is called inversion. Mass capacitor is inversion decision. Other possibilities are also there, right? Okay. Yeah, the time is up, and okay, we discussed about 2 points. Please wait for 2 minutes. I will complete it. Okay. So for example, I am putting the negative charge on top of it. What will happen? Can anyone tell me? What will happen? As we know that the realistic picture is this one. Okay. So these are the acceptor, and each and every ion has got that is equipped with holes, right? These are, sorry, electrons, right? These are all the electrons. Okay, these are the electrons, right? The moment if you apply the negative charge on top of the plate, these electrons move towards the ground side. So moves towards the bottom side, right? Moves towards the bottom side. That means these positive carriers are not available under the, sorry, these negative carriers are not available under the surface, but the surface is full of the immobile charge carriers. These immobile charge carriers, the negative ions. Okay, so these negative ions will be present under the SiO2, under the oxide. Agreed? So therefore, only the minority carriers are all available under the bottom of this this one. Okay, so normally we know very well that this is an oxide. That means immobile ions are available in it. Some other immobile ions are also added to this one. This is also treated as an oxide only now. Okay, so that means that whenever you apply a negative charge on top of this metal, negative charge on top of it metal with respect to the positive charge at the bottom, okay, because of the negative charge, the electrons are repelled. Because of the positive charge at the bottom, the electrons are also attracted. So therefore, a depleted carriers are available under the silicon dioxide. Okay, this is called actually a silicon dioxide, SiO2. This oxide is actually an SiO2. Okay, therefore carriers are depleted here. So therefore this case is called, what we can call this is depletion region. This is called depletion region. Right? So these are the two essential things that we need to understand about the mass capacitor. So this understanding is required to understand the MOSFET thoroughly, and we can develop the mathematical equation, we can understand its characteristics, how it behaves in a circuits. All those things we will see in the coming classes. Okay, I hope I'm clear to all of you that what are the different IC technologies that are available. Okay, and the important component for the IC is a transistor. The backbone for the transistor is a mass capacitor. So what are the relevant information that I have produced here, and remaining things we will see in the next class, how it will be useful. Okay, we stop here today. We see the remaining things in the next class. So Sia, can you please send me the attendance?